let's look at this in a little bit more detail. We want to use our normal distribution to give us useful information about our production. So, as we mentioned in the previous slides, there are these 2 points of inflection that are located 1 standard deviation from the mean, plus or minus 1 standard deviation. Now, if we measured all the tabletops that you're producing, and you counted all of the tabletops in the production that were within 1 sigma from the mean, so I'm going to draw this. Difficult to draw on here. So all the tabletops that are within plus or minus 1 sigma from the mean, we would find out, if we counted all this up, we would find out that about 68% of our production, of our tabletops, lie within 1 standard deviation of the mean. In fact, it's actually 68.27%. Now, if we go a little further and we look at an additional, this time on either side, 2 standard deviations from the mean, we would find that this entire area is about 95% of our production. This means that about 95% of our tabletops in our production will be within 2 standard deviations of the mean. And if we go to 3 standard deviations of the mean, we're even off my picture here, 3 standard deviations, we get a whopping 99.73% are within plus or minus 3 standard deviations of the mean. This means that almost all your tabletop widths, even though they can never be perfectly exact, never have exactly the same tabletop width, they will, 99.73% of them will have widths within 3 standard deviations of your mean width. These are the interesting properties of the normal distribution. So we'll look at this later, but what's important to understand here is that the standard deviation is a measure of the variability. As your production variability increases, as this standard deviation increases, this normal curve, this standard distribution function will spread out. And it becomes more likely that you will produce a very long or very short tables. So, again, just as a reminder, we looked last time that the integral over the normal function for the normal distribution over all values of x is equal to 1. The mean, or the weighted average of the distribution, is the mean, and the variance is the weighted average of the squared deviations of the values of the variable from its mean. So we looked at that last time. Now, let's do an example. Because often we are interested in finding the proportion of our population, for example, our tabletop widths, that lies in a given interval. So let's say the net weight of nails in 20-pound boxes is normally distributed with a mean of 20 pounds and a variance of 9 pounds squared per box. So what we do, we let the random variable x represent the weight of a box. Now, we may want to find the proportion of the boxes that have a net weight less than 15 pounds. Let's say that's our lower specification limit for the net weights. We're not allowed to sell any boxes of nails that have less than 15 pounds in them. So what that means is that we're looking for the probability that our random variable x, the weights, is less than 15 pounds. Now, the probabilities we just looked at is given by the area below 15 under the curve defined by the normal distribution function with mean of 20 pounds and a variance of 9 pounds. 20. And this would mean a standard deviation equals the square root of 9 equals 3. So we can see that also in our normal distribution function. So thus we have then the probability x is less than or equal to 15 pounds, the weight of our boxes, is the integral from -infinity to 15 of our probability distribution function. And this, if you remember, we called this the cumulative distribution function, or the CDF. So thus we can use our normal distribution function to calculate information like this. So here's a picture of it. Here's our normal distribution function, f of x. Here's x, our nails. And we're interested in, here's our spec limit here, lower spec limit. We're interested in what proportion of our population is below the spec. But this is not easy to calculate. We have to perform this integral, this complicated function. What are we going to do? Let's look at the standard normal distribution. This will help us. So if we have a random variable, which is normally distributed with the mean equal to 0 and the variance equal to 1, this is called a standard normal variable. And it's denoted by, especially for this case, not by x, by the letter z. So we can write z is normally distributed with the mean of 0 and a variance equal to standard deviation equals 1. So here we have the picture. Mean of 0, standard deviation of 1. Now, instead of writing f of x, for this specific case, we're going to use the symbol little phi of z to indicate the probability distribution of a standard normal variable. And big phi is the cumulative distribution function. So it gives you the values below a certain point. That's the proportion of the population below a certain z. Now, what's very useful about this is that the PDF and the cumulative distribution function are given as shown, and the CDF, the cumulative distribution function for values of z, has been tabulated and is called the normal table. And this, so we can use this then for performing that complicated integral. So let's have a look at how this table works. Now this is just part of the standard normal table. And you can find this in the materials that are provided with this course in PDF format. You can also find it in the book on which our course is based. And it's available in the internet if you just search under standard normal table or in any standard statistics book. Now we don't have enough space here, so we're only showing part of the table. And what we'd like to do now is to go through the table together to learn how to read it, because it looks confusing. First of all, what is this table again? It is the cumulative distribution function, big F, of the standard normal variable z, which is distributed with a mean of 0 and a standard deviation of 1. And it gives the proportion of values for the random variable z that are less than or equal to a particular value of z. So the probability that a random variable big Z would be less than or equal to a particular value of Z. So where are our particular values of Z? Here's our Z. And again, we're looking then for the proportion of the random variable that would be less than that small z. And here you can see if you look first down the left side of the table, that we have values ranging from z equals minus 3.4, z equals minus 2.8, z equals minus 1.9. In this part of the table that we're showing, we're looking at negative values for z. So that's your first step then, is to look for the value of z down at the left-hand side of the table, and then you move across the top of the table to look for the second decimal point. So here you would see 0.00, 0.01, 0.02. So let's do an example together. We have a specific value, little z, of equal to minus 2.04. First thing we do, we go down the left-hand side of the table and we identify minus 2.0. Then we go across the top of the table and we identify the second decimal point, 0.04. And we look at where those two intersect. So for z equals minus 2.04, we get a value 0.0207. So what does that mean? Again, we are looking for the proportion of values in this standard normal that would lie below a specific value. So everything, and I'm going to try to draw this, circle everything here, whoops. Everything in this table are proportions, so percentages. And what did we get? We get the proportion of a random variable z that is less than or equal to minus 2.04, that's our specific value of z, is equal to 0.0207, which is equal to 2.07%. Now what does that mean? Nice, lots of little numbers here, very confusing. Let's draw a picture at the top of the distribution function. Let me try and be very exact here. So we have our random variable big Z, which is centered around 0 with a standard deviation of 1. And I'll draw some little hash marks to indicate the standard deviation. So here we have -1 standard deviation from the mean, -2, -3. Here we have 1, 2, and 3. So all we've done is to draw our distribution function for the standard normal, and our particular value that we've chosen for this example is right about here, -2.04. I'm not very exact there, excuse me, excuse my drawing, but -2.04 is our particular value of little z. So any value that's in this shaded part below -2.04 gives the proportion of values below that value, and you can see it's very, very small. So this shaded part is going to be 2.07%. Very, very small. And what you can notice then from the table is that, for example, for z moving even further away from the mean, say z equals -3.40, the proportion that you get is very, very small. So the area under the curve as your little z value moves further away from the mean gets very, very small. And maybe that can explain also why our table doesn't need to go much further, because it's pretty much going to be nothing as the further away you get from the mean. So these in this direction, maybe I can kind of draw an arrow. In this direction, z is getting smaller. And in this direction, z is getting larger. Larger, I mean moving towards zero and then moving beyond zero. And so you can see, you know, in this lower corner of the table, you're getting 1%, 2%. And of course, as we saw some more examples, as you move to more positive Z, those proportions get larger and larger. So that's clear for everybody. Let's look at some more examples. Give us a better idea. Here we have a slightly different part of the table. Here we see our Z value. And let's look at when Z equals 0.00. So here we go down first. Z equals 0.00. We went first down here and then we went this way. And look what we get. Now that value, what did I say? In the center of the table, those are proportions. So that 0.5, when Z equals 0.00, the proportion, the probability that Z is less than or equal to 0.00 equals 0.5, or 50%. When we draw again, our standard normal distribution, mean sigma equals 1, mean equals 0. When we are right here at the mean, at Z equals 0, we know that our normal distribution, any normal distribution, is symmetric. So that means 50%, 0.5% of the population is going to be below the mean, and 0.5 above the mean. And from our normal table, of course, this is why we're seeing a 0.5 there. That's what the table shows. Let's look at high values of Z. So we start, here we have from Z equals 2 to Z equals 3.4, 3.49. Now look at these values. They're very close to 1. So for example, above 3, they're almost all, we're practically at 1. So what this is saying, it's like our tabletops. Whoops, once we get to very, very high values of Z, for example, Z equals 3.4, once we are moving a lot of sigmas, 3.4 sigmas from our mean, almost all of our tabletops are going to have widths that are below 3.4 sigma from the mean. So that's why these values are very high. And on the other scale, when you have a very low Z, you see a very small number. Okay? Let's do some examples to practice. We're going to be using this a lot in our course, so we need to make sure we understand this. This is the basis for a lot of the quality techniques that we'll be looking at. So if we have the standard normal variable Z, find the probability that Z is less than 2.62. So we draw a picture of this. We have here our normal distribution. We have Z 2.62, and we look up in the table, 2.62, 2.62. There's the proportion, 99.56% of our population will be below 2.62. Look at our picture, looks reasonable. Now let's look at the probability that Z is less than negative 1.45. We draw this again. Now this time we have a Z minus 1.45 standard deviations from the mean. We go minus 1.45. And we see that here we only have 7.35% of our population will be below the mean. And just as a note, this picture is not completely drawn to scale. That it should be maybe a little bit moved over. So let's do another one. We want to look at the other side of things if C is greater than 1.45. C is 1.45 on this side. Go back to our table, 1.45. 92.65% of our population is going to be below 1.45 standard deviations above our mean. This is the 92.65%. But we're not interested in that. We're interested in the proportion of our population that is greater. So the way we do that is we say 1 minus the CDF function, 1 minus the probability, the proportion of the population that's less than 1.25 will give us the proportion that is greater than 1.45. And 1 minus 0.926 is equal to 0.735. That's what we got before. So here we see, excuse me, this is the wrong picture. From before, we had, this is what we just calculated here. The proportion that z is greater than 1.45 is equal to 7.35%. The proportion that z is less than minus 1.45 is also less than 7.35%. Okay, now example D. Suppose we're interested in looking at the value that z is between two values, the proportion that z is between two values. We can still use our table. Here we are looking for the probability that z is less than or equal to 2.5 or greater than or equal to minus 1.5. We can do that by subtracting our CDF values. We can take the proportion here of the population that is less than 2.5. We get that from our table. We've got 99.38% minus the proportion that is less than minus 1.5, which is just down here, which is a smaller number, only 6.68%. And this will give us the part in the middle. So I hope that's clear for everybody. We have provided some more examples to practice in the exercises in this section if you'd like to do that.